So another way that we can solve our first order linear differential equations is a technique that's called separation of variables. So the idea of this one is to bring all of the variables to different sides. So I have here I is one variable, so I bring that to one side, and t is another variable, so I'll bring that to the other side. So the idea is rearrange the equation to put I and t on different sides, and then we're going to be able to integrate. So let's have a look at doing that. So I'll take my equation, I'll just combine the coefficients together, and I'll bring one of the terms to the other side. So looking at my equation, if I divide through by L, then I will get this, and if I bring the di dt to the other side, then I will get that. So here I have the I on one side and a di on the other side, so my work is not done. I need to bring the I and the di to be on the same side. So I can divide through by I, so this would give me negative 1 over I times di dt. But still I have a problem where I have dt on this side, and it's the same side as where my i's are. So here's where we have to get a little bit kind of quick and dirty with the mathematics. So I'm going to multiply by dt. Multiply by dt. And what I'm thinking of here when I do this is that dt is this little differential element, which is a small amount of time. So this is a little bit hand-wavy, and it so happens that in this scenario, this is actually a legitimate thing to do, but you need a lot more mathematics to prove that this one is actually kind of an okay strategy to follow. So I'll just show you how it works, and you have to kind of take this one as a little bit of a leap of faith. So in order to solve this equation, what I would like to be able to do is integrate on both sides. And when I go to integrate, I'm going to end up with this kind of a little bit tricky integration here. The idea of this, it's like an integral substitution. The idea of this is that I can kind of substitute the variables and eliminate the t and end up with just the I. So algebraically, you could imagine that you're actually kind of cancelling top and bottom here, but that's not the correct mathematical way to think of it. These are like di dt is not a fraction. You can't just cancel top and bottom on that fraction, even though that's kind of what it looks like when we do this simplification. So as I say, I don't really like this method because it is a little imprecise, but basically we end up with this. And this now is something that we can integrate because I can integrate left and right hand side separately because I just have a plain old variable in each case. So integrating here, I will end up with, on the left hand side, I will end up with r over L times t. And I should include a constant of integration here. So I'm just going to go like a plus c, which is my arbitrary constant of integration. On the right hand side, the antiderivative of 1 over I, so this is going to give me the natural logarithm of my current variable. So you should remember that integral 1 over x dx is equal to natural log of x. So you should remember that as one of the kind of fundamental integrals that you should know. So at this point I can solve for I can kind of simplify this equation a little bit. So if I bring the minus to the other side, then I will have the following expression. So it will be negative r over L t minus c, and therefore my current expression I, taking the exponential of both sides, is going to be negative r over L t minus c. And if you know your rules for exponentials, then you can actually simplify a little bit here, just split off this like e to the minus c term. And then this thing here, this was an arbitrary constant of integration, right? It's an arbitrary constant of integration. I don't actually really care very much what is the value of c. So I could replace this with some other coefficients. So let's just pick letter A is equal to e to the minus c. And so by doing that, what I will end up with is a times my exponential negative r over L times t. Then the final thing that I need to do is use my initial condition to find what is this constant of integration here, a. So next, use the initial condition to find the constant of integration. So remember, we had, when we analyzed the circuit, we had that the current at time 0 is equal to some number that we get from analyzing the steady state circuit. So we can substitute t equals 0 and I0 is equal to what our initial condition was. And if we do that, we will get the following expression. So I'm looking here, so I've got I of t. I'll write I of t just to make it super clear. This is a time varying function. So left-hand side gives me the constant, which was my initial condition. Right-hand side is going to give me a times exponential of this thing, which is times 0. And of course, exponential e to the 0 is a 1, excuse me. E to the 0 is a 1. And so therefore, my constant of integration is equal to the initial condition for this particular case. And therefore, the solution is that I of t is equal to initial condition I0 times our exponential of negative r over L times t. And that's the same solution that we got before using a different method, and we should obviously get the same solution no matter what technique we use to solve it. But this is another way that you can approach solving differential equations like this. So to recap, the idea was rearrange the equation to put the variables on different sides. So the variables are the function and the, in this case, time, so current and time. Rearrange, and the little bit that requires kind of the leap of faith is the idea that you can substitute or simplify this integral down into just being an integral with respect to I.